Good afternoon, everybody. Everybody still awake? Good. Let's see where we can take the revolution evolution thing. So I'll start with the revolution and we'll get to the evolution afterwards. So kind of the current state of data stores is, maybe some of you know dbengines.com. They have like the Tioba index for programming languages. They do the same thing for data stores. And currently, the February edition looks something like this. Oracle is still sitting on top. Then we have MySQL. We have MongoDB as the number one NoSQL store. And then we have following Redis, Elasticsearch, Cassandra. And I'll kind of take you through the story a bit, like how Elasticsearch got up to place 9 here. That is kind of the revolution part. And for the evolution part, we'll do some hands-on demos like what we've been trying to change recently. And yeah, you can always discuss about this list. I think it's pretty reasonable except for this one here. I'm never sure why this is on here, especially if you see stuff like that. The statement is too complex. Yeah, I don't think it qualifies as a data store. But anyway, so who uses Elasticsearch? Yeah, that's a good number. I like to see that. Who is already on version 6? Very nice. Who is still on version 2 or 1? Okay, I'll try to give you some motivation today why you might want to upgrade as well. So we'll see. Why am I talking about that? I work for Elastic, the company behind Elasticsearch and the other open source products we have. I'm part of our infrastructure team. We do stuff like the Docker containers, internal testing, any automation, clouds. And I always say this is a Unix pipe. I kind of pipe that into developer advocacy. So I try to talk about the good stuff that we do. So how did it all get started? Shai, who started the project and is now our CEO, he started blogging at thedothebytes.com. That was his blog, and it's still up. And he has a blog post how it all got started. And in the beginning, the product wasn't called Elasticsearch, but it had 2 predecessors, which were called Compass. And how he got started with Compass was his wife wanted to become a chef, a cook. And she moved to London. And as a good husband, he tried to help his wife. And she had lots of recipes. And he wanted to write some system to search her recipes. And he kind of over-engineered that, because that's how he got into the full text search stuff, and she's still waiting for that recipe search, by the way. It's kind of the running joke internally when he will ever finish that. But he says, like, at the moment he's a bit too busy. But maybe at some later point we will, somebody might do a recipe search for him, so we can kind of move past that. And he started off with Compass 1, and then he totally rewrote that, calling it Compass 2, and instead of having another rewrite calling it Compass 3, he called it Elasticsearch afterwards. And everybody knows 3 is kind of the lucky number, so that one stuck, and that is what is kind of widely used, or the most widely used search engine nowadays. So that was the initial logo. Our Photoshop skills have slightly improved since then, but this was the initial Elasticsearch logo, and back then Shai did everything. He wrote the code, the documentation, the website, he answered all the questions. At my previous company, we always called him the search beast because he was always doing something about search and he was super productive. And yeah, stuff developed pretty well. And you can see this is the Fiverr version, and he gave the product the tagline, "You know for search." It's also in the title, that's kind of like the core of what Elasticsearch is about, or at least where it got started. So if you're searching anywhere, there's a good chance that Elasticsearch is kind of doing the search for you. If you're searching on any of these sites, behind the search box, there's Elasticsearch doing the actual work for you. We're not responsible for the actual kind of quality of those. It's kind of an implementation detail then. Anyway, so this worked well, and then people figured out that there is more stuff that is actually a search problem. So people figured out we want to have some visualizations of the data we have in our system. And then people came and said, like, oh, we want to put logs in there, because having logs is kind of a search problem as well. We want to collect our logs somewhere, put them in a system, and then be able to search for all the errors or whatever happened in the system. And then kind of Elasticsearch joined forces with Kibana and Beats, Kibana being the visualization and Logstash being the part to get data in. And together they formed the famous or infamous ELK stack. You can see Elasticsearch, Logstash, Kibana, and yeah, ELK, you get it. So that was the ELK stack that is also working very well and is widely used. Here are just 3 very common examples who are using the ELK stack for log aggregation or security analytics. So Mozilla has an open source product around security analytics or SIEM. Slack is using it internally for all the log aggregation, and Blizzard, if you're playing any Blizzard games, they're also doing or aggregating all the events in the stack somewhere. And that was working well until we added another component. This is Beats. It's kind of like a lightweight agent or shipper or forwarder written in Go, because Logstash was Ruby and now JRuby, and it's always kind of heavy. And telling people, if they're not a Java developer, to put the JVM on their nodes just to collect logs, that wasn't really what made people happy. And then kind of the ELK had to evolve. And it thought about it, and the ELK had to develop. And then it said, like, maybe I'm an ELK-B personality. Because you see, Elasticsearch, Logstash, Kibana, Beats, that's the ELK-B, or sometimes we also call it the BELK. And you can see it's the B and the ELK horns. However, since we're always about scalability, even marketing figured out that this is not very scalable, because what happens if in the future we add another open source product? Then we need to probably add another letter, and then we need to make up another animal. And A, it will get harder to make up animals of more letters, and B, then you need to do the rebranding. And rebranding is always like, I always have the feeling rebranding takes like 10 years. So still a lot of people are saying ELK stack. And it's totally okay, we get that. We are just trying to push the name a bit forward. And what we've gotten to is now we just call it the Elastic Stack, because that's super scalable. Whatever open source product we have, we can just put it into the Elastic Stack, it will still be the Elastic Stack. So that's why we call it the Elastic Stack. And that was kind of the revolution. So now it's time to get to that evolution. What is going on in the evolution? Before we dive into the demo, just to make sure that everybody is familiar with a few terms, cluster is like all the different nodes working kind of over the same data. So you can query that cluster, and it has spread out the data internally, and you can query it in that cluster. A node is basically one JVM process of Elasticsearch running as part of that cluster and doing the actual work. Then you have an index. An index is basically a collection of stuff that is kind of similar and belongs together. In the past, we have said it's similar to, maybe a table in the relational world, but that is a very bad comparison, and we don't want to say that anymore. But it's something kind of, some things that belong together. Every index is then made up of shards. Shards are just like split up parts of an index. And that one is actually then Apache Lucene writing the data in the background to the disk, because often people ask, like, what is the data store behind it? There's no other data store involved. Lucene is actually writing the data to disk and doing the kind of heavy writing, reading, querying. And Elasticsearch around it provides the REST API, the query DSL, and all the sharding and replication of the data. The smallest thing you're normally writing is a document, and every document has an ID. And that ID will be hashed to make sure, or to know into which shard we will write that document, and then you can search over it. So these are kind of the base terms. If you know these, you're pretty much good for that demo. So we kind of like to compare that to a person growing up. That software is also like a person, it's also growing up. In the beginning, it starts a bit like a toddler and has a lot of potential and can develop in a lot of directions. And along the way, you learn stuff and you improve, and it's a continuous learning process. And I'm not exactly sure at which stage Elasticsearch is right now, if we're kind of teenagers or if we're kind of like in the 20s or 30s, but it's kind of developing. And that evolution part now, we want to see a bit of that evolution of what is going on in Elasticsearch. So the first thing we have learned is strictness. In the beginning, when you start a new open source product, what you want to have is, you want to have it to make it easy to use that product. And that's what we did. Like, whatever data you gave us, we tried to store it. Even if there was some syntax error, we tried to work around that just to make it easy to get started. But as your systems mature and you get more production users, at some point you start valuing more strictness. So you catch errors early on, and there might be a bit more pain upfront, and it might be slightly harder to get started, but it will take out a lot of the pain afterwards. Yeah, so if you're doing bad stuff, don't do that. We have learned we're trying to avoid the bad stuff, and we'll tell you upfront, that's bad, don't do that. So the first thing I can quickly show you, I'm querying everything through Kibana, because it has a kind of nicer way to query stuff, but you can totally do the same thing with curl as well. Is that large enough for the last row to read? Good? Perfect. So what I have here is I have the latest 5 version of Elasticsearch running. It's 5.6. I have 3 nodes, which is a bit hard to read here. But you can see I have 3 nodes here, Elasticsearch 1, 2, 3. One is the master node, that is this little star here. And my cluster is generally happily running. It's in the green state. Everything is good and working well. So the first thing I wanted to show off was the strictness. Can you see the typo in here? Yeah, it's hard to see. And even for us, it was often hard to see typos like that. And in earlier versions, what we would do is, if there was a typo and Elasticsearch didn't know a specific parameter, it would silently ignore that. And we would do the same with configurations. And if you have a 150-line configuration file and you have some typo in there, that is very annoying to try to find out. So what we have added now is, if something is misspelled, Elasticsearch will actually tell you what is going on. And thanks to the Levenstein distance, we can actually tell you, this here we don't know, but there is something else that we do know, and that is, maybe you mean tokenizer. And tokenizer, if I can spell it, it is deprecated to use it like that, but now at least it works. And it will tell you, okay, this is the right way to do it. So strictness, we kind of learned that this is very helpful if you actually show the errors up front. The other thing we have added in 5 was the so-called bootstrap checks. So if you have like a node that is badly configured, and we know that you will have problems in production, we will not start up that node as soon as it can form a cluster. We always assume if you're just running on localhost and you're not clustering it, or there's no way to cluster it, is it a development instance? We don't really care. But as soon as you can form a cluster, we assume this might be a production system. And we will actually tell you there is something very wrong here. For example, you don't have enough file handles. Or you're using a specific Java version where we know that the garbage collector might add corruptions to your data. And we would rather fail early and tell you up front, like, hey, this is not working, do something, than fail later on and lose your data, and then everybody is super pissed. And also our support is happier if we can avoid stupid mistakes early on. So these bootstrap checks are actually making sure you kind of avoid common error scenarios, and there is no way to circumvent that. Because at first we thought, well, we could add a flag like override that, I don't care. But then what everybody would do is just run in production with the flag like don't care, and we wouldn't have gained anything. So there's no way to avoid that. Bootstrap checks are here to stay, and they will be enforced. Okay, what if you want to upgrade? Let's upgrade to version 6. So we'll try to do a live major version upgrade, and I'll actually upgrade to an internal build which is not yet released. So let's see how that goes. I guess if that works today, we can actually release it to production. Okay, so the first thing you want to do is if you want to migrate from version 5 to 6, we have a new tool which is called the Upgrade Assistant. And the Upgrade Assistant actually, first it tells you, please back up your data. Always do that. I will skip that since I don't have any proper data in my cluster. I will skip the backup. But if you do that in production, please do it, or don't complain to us at least. Okay, and then we have these cluster checks. And the cluster check is basically telling you, here's something is wrong. Here I have in the .kibana index, which is kind of like an internal index, storing what is going on inside, or like what is configured in Kibana. That needs to be changed. And it could either forward you to the documentation to tell you which commands to run, or we have this reindex helper here, which can actually do that for you. For example, here you can see here that Kibana index. We can re-index, and it will automatically fix all the stuff you need to upgrade in the background for you. And it told you, okay, I have done that. If you refresh that here, you see we don't have any indices which need an upgrade anymore. And if I go to the cluster check, you can see, okay, everything has been done as we needed. Okay, so before we do the actual upgrade, I will quickly insert these 3 documents. We'll come back to them later, so you might want to remember them. What I have here, I have 3 documents. They're all in the index types. So this is the index types. They are of the type 1, type 2, type 3, and then they all have the ID 1. And we'll just store them, we'll get back to them. We'll see another thing that we have changed, and we'll need those later on for them. So let's insert our 3 documents, we have done that. And now we can actually start upgrading stuff. So I have this running as a Docker container, and we'll simply change in the .env file, I will switch over from the 5.6.7 version to 6.2.0, which is not yet released. Like the current stable version is 6.1.3, but 6.2 will also be released relatively soon. But you know, you always need to test your upcoming releases. Today is a good opportunity. So we are changing that to 6.2, and what I will do then is I will basically shoot down the node 3 I have here, and this will be replaced with the new version. So let's run this. It will basically kill the node and recreate it in the background. And you can see here, Elasticsearch 3, let me scroll up here, exited with code 143, so this was just killed. And it got a new color, it's starting up again. In the meantime, we can keep querying that cluster. So you can see right now we only have 2 nodes in the cluster, 1 and 2, which are 5, 6, 7. And you can see Elasticsearch 3 already came back up and joined the cluster. And this is now in version 6. And while this looked super simple, this was one of the main pain points we had in the past, because a major version upgrade always meant taking down the entire cluster and then upgrading all the nodes and then restarting them. And now, from 5 to 6, we have this mixed version. So you can do an upgrade with a mixed version 5 and 6, and we can just rotate one node by the next until everything is upgraded to version 6. And in the meantime, let me quickly kill the node 2, and I can show you that we can keep querying the data in the cluster. So you can run this. You can see right now I have 1 and 3. 1 was the master node. That might take a little longer when we kill that one then. And you can still read your data and write your data even though one of the nodes just was kicked out of the cluster and is being restarted. And if I entertain you long enough, that node should join the cluster soon again, hopefully. Yeah, so you can see 2 and 3 are already on 6.2. So we can now upgrade the final node. The one thing I need is I need to copy out the curl command. Kibana is always connected to one single Elasticsearch node. So when I upgrade the Elasticsearch 1 node, this is who Kibana is talking to. Kibana will not be usable, so we'll need to fall back to curl in the meantime. So let me kill or upgrade the Elasticsearch 1 node. You can see here stuff is happening in the background. When I try to reload that page, it will fail because, well, I cannot reach my Elasticsearch node anymore. But we can still check on the command line. So if I run the curl command, you can still see the cluster is still working as expected. Elasticsearch 2 has become the new master node now. The ports were 9201 was Elasticsearch 1, the 2 is Elasticsearch 2, and 3 would be Elasticsearch 3. So this is working, and we're basically waiting for the node to join back. So it's back. We can switch back to Kibana. Let's refresh that one. We just need to scroll down here to the right place where we had that. Yeah, our data is still there. The cluster has been fully upgraded now. The remaining thing we need to do is we need to upgrade Kibana. So let's run that. I'll just kill the Kibana node. And everybody who's complaining about Java taking a long time to start up again, Let's wait until that node process comes back. Because I always have the feeling that that one node thing is taking up the most time. So we have killed Kibana. Kibana will be gone if we go here. Page is not available since Kibana is starting up again. The cluster, in the meantime, is happily working in the background. So you can still run your queries, just Kibana is not available. And you can see it exited. And it's starting up again, and it will take some time until, I don't know, 1 million NPM dependencies are being loaded. I still love the Kibana team, but yeah. This might take a while. Anyway, so we have fully upgraded the major version now, and now we will be at version 6. And you can see Kibana also slightly changed its color. I always say 3 was black, 4 was white, 5 was colorful, and 6 is blue. But I have been told that this is much better readable if you're visually impaired or colorblind, and like contrasts are better, so this is the new thing. So this is what you want. And you can see major version upgrade done. Everything up and running, no problems there, so that was surprisingly easy. Let's continue with other features. So this was basically the upgrade. The train is running, you're just laying the tracks while you run on them. That's pretty much the rolling upgrade we've added. So that's a kind of nice feature. So other security things in the context of not kind of destroying your cluster are flood stages. If you have used previous versions before 6, there were 2 flood stages. So flood stages pretty much are, you don't want to run into something and everything falls over because you run out of disk space. So we always had the low and the high watermark, we called them. So the low watermark was basically we would not allocate a new shard on a node if more than 85% of its disk space were used up. And once you have reached 90% of the disk space of a node, would try to actively migrate shards away from that node. Problem is, if there is no more space in the cluster, it cannot go anywhere else. And what we didn't do is we never stopped writes. So if you kept writing to a shard that was on a node, at some point we might run out of disk. And I guess everybody knows if you run out of disk, it will be a pretty shitty day. And we're trying to avoid that now. So we have added the flood stage. The flood stage will basically reject your writes once you hit, this is the default setting, more than 95% of the disk space used. So if you only have 5% of the disk left, we will reject your writes rather than potentially corrupting your data. And I can very quickly show that as well. Let me scroll here. So I'm adding a new document into the index myFlood. And we can check how much disk we have left. You can see here we have total bytes, free in bytes. We have all the statistics. And what I'm setting now is that laptop has 250 gigs of disk. So if I set the flood stages to 400, 350, and 300 gigs, I will hit all the flood stages immediately. And that will refresh after 10 seconds. So let's apply that. We have set the flood stages. I can still read my documents. We need to wait for 10 seconds until this setting is applied. But my write should now be rejected. So if I write here, it will actually tell me it was forbidden. You can only read data or you can delete data, but you cannot update or index new data. So those are not allowed because otherwise you might run out of disk space and corrupt your data. So we kind of turned that off. Let's revert those settings. So in version 5, I think we added that to just set something back to the default value, you set it to null, and all the settings will be reverted. So should this command now work if I try to write another document in there? Any guesses? Who thinks this will work? Who thinks this will fail? The rest are undecided. Okay, so the thing is, once a class or a node, so if a shard of an index has been on a node that has hit that flood stage watermark, we will lock that entire index, and you will need to unlock it to re-enable writes. So if I run that, it will fail because it's still in the locked state. I need to unlock it by setting that index blocks read only allow delete. I reset that basically. Once I reset that, then I can write documents back into my index. So this is a little trap you need to be aware of. Once you hit that flood stage watermark, you need to kind of re-enable the index for writing again. Otherwise, we will not allow writes. Okay. This is one of the things that will protect the data in your cluster, even though it will reject new writes. But we think this is kind of the right trade-off. The next very big feature we have added are sequence numbers. Sequence numbers are basically keeping track of every change you do in your data. And add some sequence number to that. And this is actually surprisingly hard. So let's see what this is giving us. Just to give you an impression of what is going on behind the scenes. So we have the primary shard here, and you're writing data to the primary shard. And then that data is replicated. We have 2 copies here. We are replicating that data. The yellow line is a local checkpoint. And with every write, we kind of piggyback on the acknowledgement back with the local checkpoint, and then we can advance the global checkpoint. So you can see we have written 2 and 3 now, while writing it out, and the acknowledgement back is basically telling the primary shard that those have been acknowledged, and we can advance the global checkpoint. And now we write 4, 5, 6, and then the primary shard dies, or the node with the primary shard dies. And the replica shard 1 gets 5 and 6, and the replica 2 gets 4 and 6. This one is promoted to be the new primary. It has never seen the 4 update, so it tells the other node, get rid of that 4 update and only apply the other ones. So this makes sure all the data is synced up, and we don't have any phantom writes or stale writes. This is kind of, for the integrity of your data, a very important thing, and it makes keeping everything in sync much easier. And you can actually demo sequence numbers, which sounds kind of hard, but it's actually not that hard. So I'm creating a new index. This new index has 1 primary shard and 1 replica shard. How many shards do we have in total? Who is for 1? Nobody. Who is for 2? Who is for more than 2? No, it's 2. It's 1 primary shard, and if we say replica, we say 1 other copy. So it's 1 primary shard and 1 replica shard. And since I need to kill nodes again, and I still want to keep using Kibana, I say this data cannot be allocated to the Elasticsearch 1 node, because Kibana is talking to that specific node. So this index, 1 primary shard will be on the Elasticsearch, or one shard will be on the Elasticsearch 2 node, and 1 shard will be on the Elasticsearch 3 node. But I can show that in a moment. So let's insert that data. It has been acknowledged, and then we can actually check out, okay, we have 2 shards as promised. You can see the primary shard, that is that P here, the primary shard is on Elasticsearch 3, and the replica shard is on Elasticsearch 2. Remember that Elasticsearch 3 is the primary shard. We will need that knowledge in 1 minute. And I will probably forget it, so I will ask you. And then you can start inserting documents. And if you have seen inserts in previous versions, this block here looks very familiar. This one here is new. So we have a sequence number and a primary term. The sequence number is basically the number of write operations. So if I do another write operation, this will be incremented here. The primary term will change every time the primary shard changes. So when I kill the Elasticsearch 3 node later on, that primary term should change. So let's do some write operations. So you can see the sequence number keeps changing. That's all easy. If I take a specific document here, for example, the document 1, and I insert it, it increments. Do you think the increment also increments when I do the same operation again? Yes, it will, because it's just an in-place update, so this will replace every version. If I delete that document 1 again, if I delete it, okay, it increments the counter. If I delete it again, nothing changes. Will it increment the number? Yeah, it does. So we are keeping track of all the changes that you send to the cluster, even if we have already applied them. We don't really care about what they do in the kind of like in the effect afterwards. It's just like counting these operations. Okay, which one was the primary shard? 3. Right. So we will kill the 3 node. Since this is randomly allocated, let's kill the 3 node. And then you can check. And you can see now the new primary shard is Elasticsearch 2. And the replica shard is unassigned. Why did we not allocate it on the Elasticsearch 1 node? Because we had the shard filter where we told it could not go there. Why don't we allocate the replica copy on the Elasticsearch 2 node as well? Because we don't win anything. We never allocate the replication on the same node, because if that node goes down, both the primary and the replica shard will go down, and you have just wasted half of your disk space. You would not win anything. So that was easy. We can keep indexing new documents. Let's keep track. 1, 2, 3, 4, 5. I've inserted 5 new documents, which was only going to the primary shard now. Let's restart that node. It should join as a replica node again. So it will take a few moments until that one comes back up. So right now the replica shard is unassigned, but in a moment, once that node comes back up, the Elasticsearch 3 node should be the new replica shard. And Elasticsearch 2 will stay my primary shard. And let's hope the demo gods are with me. Let's check. Okay, it says started, so this should be good. Let's check again. Yes. So you can see Elasticsearch 3 is now the replica shard. Everything went as expected. And now comes one of the big improvements of this approach. When I run this command here, which says, tell me how we did recovery-wise, it will tell me, I'll scroll this over a little. You can see Elasticsearch 2 to Elasticsearch 3 recovered 5 documents. Those were exactly the 5 documents I inserted, while the primary shard was there, but the replica shard was not there. And what we were doing in 5, or in Elasticsearch 5 and earlier versions, was we would do a file-based comparison. So we would compare the Lucene shards, and since we were writing them independently, these Lucene shards were often totally different. And we would basically, I think, take a hash of them, and if the hash was not the same, we would just copy that file over. So if one node was just kind of leaving the cluster for a minute, you might need to transfer gigabytes of data for no good reason other than we didn't have a good comparison way or way to replay the missing operations. With that transaction log, we're actually keeping track of all those write operations, and we can recover and replay just those 5 operations that we have missed. So that will make flaky nodes or just adding nodes that have been disappearing for a short amount of time much simpler and more performant. Downside is we need some more disk space because we need to keep track of that transaction log. Keep that in mind when you kind of plan for the disk space you have. Okay, let's delete that index and recreate it. This time I'm setting it to 10 shards and 1 replica. How many shards do I have in total? 20, hopefully. Let's see. If I check the number of shards and make this a little smaller, you can see 20 shards, 10 primary, 10 replica ones. And now we can keep adding documents. And the confusing thing is keep track of the sequence number for a bit. Now we are at 0. If I run that again, 0 again, 0, 0, 1, 0, 0, 0, 1, 2, 1. Any ideas why this might happen? Yes. The sequence numbers are per shard. So every shard keeps track of the operations. If I say this is the ID, I want to insert it, the ID will be hashed, it will always land on the same shard. So if I keep using that one, it will always go to the same shard, and this will be a nice increment. Like it will just, every operation will go to the same node and will keep incrementing. So that's easy. So both the recovery is much more performant, and this feature will also allow totally new features in the near future. Yes, the other thing, especially Postgres, people often ask, like, what if you reach kind of the end of that number? Because Postgres has this concept of, is it the transaction ID, I think, which is an integer, and if you hit that limit, your cluster will go down in a very bad way. So people are often concerned, like, how do we roll over that number? and we don't. For two reasons. A, this is not a global number, but this is per shard. So normally you will have quite a few shards on one node. So there should be some room. And B, this is not an integer, this is a long. And as Bill Gates would say, is 63 bits is probably enough for your increments for a long time. And we don't plan for anybody to, or we don't expect anybody to run into that. I don't know how many write operations you would need to do for a few years to run into that, but it's definitely a lot. We don't see that as a problem. And the other thing that we will, or this feature will allow in the near future, this is under heavy development, so I'm not promising any version numbers. It's 6.x, or it might even be 7.x, we will see, is cross-data center replication, because we have the transaction log, and we can then just replay those transactions to a different data center without adding any big latency in the communication. So this will enable great new features in the future. Now this is the thing that a lot of you might have seen, and this is one of the main hurdles for upgrading, or perceived hurdles, is that types are going away. Who heard that types are going away in Elasticsearch? That's not that many. So let's try to clear that up and see how we can do that. As you can see in the version number, this is a very long-term thing. We try to make this as painless as possible, and it will take multiple years until we finally reach that. But first off, why are we getting rid of those types? The thing is, we kind of lied. Because this type thing never really existed. We made it up. This was when I said at the beginning, in the beginning we tried to say, well, it's very similar to relational databases, because an index is like a table, and that was just not a very good comparison. And then we had the type, which you could have in the different types. And it wouldn't match together. Lucene doesn't have that concept at all. And you would run into three specific problems if you were using multiple types per index. The first thing is, since Lucene always sees the field name, all the data types for one specific field name in one index need to be the same. So for example, if you have a user which has a field disabled, and you think in one type it's a Boolean flag, and in another type it's a date when you disabled the user, this will not work, because it needs to be of the same type. Secondly, sparsity is not that great in Lucene. Lucene 7, which is in Elasticsearch 6, improved that, but it's still kind of a thing. And finally, scoring always works, kind of the quality attribute of searching always works across all the types. And that was also confusing. So we're trying to get rid of that artificial concept of types. And this is actually the plan of what we're doing. In 5.6, you can opt into the single types. So there can only be a single type per index. That is, you can actually enable that in the configuration. In 6.x, we will enforce that. So by default, every newly created index can only have a single type anymore. If you import an index from a previous version, it can still have multiple types. But any index you create can only have a single type here. In 7, the type will become optional in the API. Since we assume that you have only a single type there, it can be optional. And in version 8, the types are finally gone. So this should allow for kind of like no hard upgrade changes or like no breaking changes in the upgrade path. But it is a kind of like a multi-year process, and we will try to get there. So how do you upgrade stuff? You remember the three documents I have inserted in the beginning. I had, in the index types, I had the types type 1, type 2, and type 3. Since they were created in Elasticsearch 5, you could just insert them and everything is working as expected. Now, if I create a new document, I create in the index no types underscore doc. This is the one we are kind of proposing. You can pick any type. It just has to be a single one. But the one we are proposing is to use underscore doc. Since this is kind of the default we will expect in 7 then. So I am inserting a document with that type doc here. What will happen if I try to insert that document now as well? Then I will run into the error that it says like, oh, you would have multiple types in that index. We already have underscore doc, and you want to add that other now. This will not work. I'm rejecting that. And the other big question is, how can I actually migrate my existing data to that new single type approach per index? So what you do is we have that nice reindex API where you basically can take documents from one index and replay them into another index. And we can also change them in that replay thing. So I'm taking my documents from my types index and I replay them into the no types index. And I also run a script against that where I do the following change. I change the ID to type plus ID. Since all my 3 documents in like each of the types had the ID 1, I need to do that. So I need to concatenate type and ID to get a new unique ID. I say the field underscore type, which was this kind of magic field, I just transfer that to a custom field type. So this is just like any other field, but you can still efficiently filter on that, for example. And I say the new type I set for all the documents is underscore doc. That is the one that I had when I created the index. So when I run that, it will insert my 3 documents that I had in the types index. And if you search in that no types thing, you can see it has all the documents that we had before. So it had the no types doc, that was the one I inserted. But here you see in the no types, I had that one that was the type 2 with the ID 1. And it replayed that, and now everything is down to a single type. And that is how you can migrate your data. So either you have like some temporal data and you just throw away the old data, then you just switch to a single type pattern. Or if you have like more of a search use case where you keep your data for a prolonged time, you can use the reindex API to just replay stuff to see how it's going. Okay, and we're down to nearly the last one already. These are just 2 things without the demo. These are nice performance improvements we added. The one is automatic queue resizing. So what automatic queue resizing is, when you do a lot of operations, they will queue up. And we wanted to have kind of like a way to guarantee that your queries will respond within a certain amount of time. And either they can be done within that certain amount of time, or they will be rejected. And this query resizing actually makes sure this happens. So for example, here I say, the target response time for my searches is 2 seconds. And if you are currently processing 50 requests per second, your query depth, your queue depth can be 100 elements. And if you try to add 101 elements, that 101st element will be rejected, or 101st element will be rejected. So we will rather reject the write than queue it up for a very long amount of time. And then your client can decide what to do, retry that operation or do something else. That is the adaptive queue sizing, where you can basically guarantee a response time. Rather than queuing up, we will reject an operation and you can then handle that in your application. And the second nice thing is adaptive replica selection. Right now, if you search for data, you can either go to a primary shard or any replica shard. And we will just randomly select it and pretty much round robin between the shards. However, what happens if one node is busier than other nodes? And the adaptive replica selection is exactly doing that. It's based on a very nice paper where they actually found out how you can kind of weigh how busy a node is, and you will send requests always to the least busy node. So your queries are running faster. So yeah, you have this exponentially weighted moving average, and basically when doing your requests, the node will tell you in the response how busy it is, and then your queries can select the least busy shard when doing queries. And we've done some benchmarks. In most of the cases, even for the 50th percentile, it's improving. But at least in the 99th percentile, all the scenarios we tested, if you enable that setting, it will improve. In 6.1, at least, this is disabled by default, but you can enable this feature to kind of try to pick shards more cleverly. The other thing is shrink and split. We haven't had that for a long time, and we basically said we will not do split ever. We changed our mind. We just added split in 6.1. So let's take a quick look what they're doing. So shrink is basically you have too many copies and you want to combine them. And hopefully stuff works out and it doesn't end like this. So yeah, how do we do the shrinking? That's not what I wanted. The shrinking is basically you always combine a number of shards by a factor. Is 5 a good number of shards by default then? Not really, because 5 is a prime number. So the only factor to which you can go is, divide by 5 down to 1. So let's quickly demo that. So we have an index called shrink. Since I have 5 shards by default, 5 primary shards by default, it will create that for me. If I show the shards, you can see I have 5 primary and 5 replica shards, so 10 shards in total. And then I say, before you can actually do that, you need to tell that index that all the shards that you want to combine need to be on a single node. So for example, here I say all of the shards need to be on the Elasticsearch 3 node, and you cannot write to that anymore. Because what is happening in the background is to make that operation very quick, we're basically hard linking on the disk all the different shards that we have. So that operation, once you have everything on a single shard, is super quick. So let's run that. We have done that. We can show now here, I'm sorting that by shard, and you can see every shard is either the primary or the replica, at least one of them is on the 3 node now. And now I can run that operation where I say, take the shrink index, run _shrink, and write the result to the shrunk index. So the data will then be written to the shrunk index, and go down to 1 shard. So it runs. And I can then query the shrunk index, or here is the number of shards. So we have 1 replica, 1 primary shard, and they can go to any node again now. Elasticsearch 1 or Elasticsearch 2 are fine. If you query that, you can see we still have our data. And we can also go the other way. So we can also split data. Splitting pretty much looks like this. And that's why we always kind of said this is a very violent operation, and it's very heavy, and that's why we don't really want to do that. But we have now made some preconditions. The precondition is you need to define the factor into which you can split it up front. And we kind of synthetically have these different shards then up front, but they're kind of packed together. So you don't have any overhead for them in the beginning, but you can split that up very efficiently and easily afterwards. Just to show you what this looks like is, here I create my index split with 1 shard, but in the background it has 20 of these to be split up shards. So we have created that one. I'm inserting a document. And then I say, this has 1 primary and 1 replica shard. This is what you expect. I block writes again. You always need to block writes when you do an operation like that. And then what I'm doing is I say, take the split index, call the _split on it, and store the result in the split in 5 index. And here I say the split in 5 index basically has 5 primary shards. So if you run that, and then check the shards, you can see now we have 5 primary and 5 replica shards. And the document we had in there is still available. And this is how we could break that up. So that operation here, the index number of routing shards, pick a good factor that you can split into a lot of different indices or number of indices which you might be interested in. Don't pick a primary number here. That's not a great choice. Okay, finally, benchmarks. Benchmarks are kind of an ongoing theme. This is my favorite comic whenever I see benchmarks. So whenever you see a benchmark of somebody doing a benchmark against themselves and some of their competitors, this is pretty much what they are doing. They pick some similar conditions, and their own product is much better in those similar conditions than the others. It always reminds me of, I think 2 years ago or so, MongoDB, Cassandra, and Couchbase each made a benchmark against their 2 competitors, and each one of them did that, and each one managed to find some scenario where they were at least twice as fast as the other 2. And everybody did that within the span of 3 months or so. And that's pretty much the value of all the benchmarks. What you should do instead is benchmark very heavily internally. We're doing that to avoid the slow boiling frog problem. Everybody aware of what the slow boiling frog problem is? If you throw the frog into the boiling water, it will jump out because it knows something is wrong. If you put the frog into the cold water and then slowly turn up the temperature, it will not jump out because it doesn't recognize it. And you have the same thing for benchmarks. So you need benchmarks which tell you, okay, this change made everything 0.5% slower. And this other change made everything, I don't know, 1% slower. And over time, these would accumulate. So you will need to very aggressively benchmark that you don't have this slow boiling frog problem, that you don't even recognize what is going wrong. And we have written our own benchmarks, or benchmarking tool, and we even publish those all the time. So you can see what every single change is doing to the performance of the system over time. So to wrap up, we have seen quite a lot of stuff in action. It's kind of the growing up of Elasticsearch. We got more strict. We tried to make upgrades less painful. We tried to make your data safer. And we tried to add new features like the sequence numbers with the cross-data center replication. Sometimes we have to make hard changes like removal of types, but in the long run it will be a good change because we need to clean up that lie, basically. And then we have seen some performance improvements, and shrink and split. Those were two things that people requested for a long time. And especially the split is we slightly changed kind of the preconditions, and that now enabled a totally new feature for us. And that's pretty much it. So I always take a picture with you so I can prove to my colleagues that I've been working today. Because nobody knows where I am normally. I'm just doing conferences. So everybody say Elasticsearch. Very nice. Do we have time for questions? Okay.